In the last lecture, we looked at some examples, classical examples of applications of graphs. In this lecture, we're going to look at some classical examples of digraphs. We'll see an ecosystem, a prerequisite, a binary search tree, and we'll also look at a Markov model. Our first example is the ecosystem digraph. In this example, there is a directed edge from animal 1 to animal 2 if animal 1 will consume animal 2. For instance, at the bottom of the graph on the right, there's a garter snake and a directed edge from the garter snake to the frog, and this implies that a snake will eat a frog. But of course, a frog will not eat a snake, and so the direction is one way. In many applications, the relationship is just one way, and we need to indicate that with a directed edge. As a student, you're familiar with the concept of a prerequisite for a course. So this diagram tells us at a glance which courses are a prerequisite for which courses. So for example, Math 151 is a prerequisite for Computer Science 220, and so is Computer Science 150. It's a prerequisite for Computer Science 220 also. From Computer Science 220, there are two directed paths to Computer Science 490. We can go from 220 to 360 to 490, or we can go from 220 to 477 to 490. So the instructor of Computer Science 490 can assume that all of the students have had either 360 or 477, but not necessarily both. Now, can the instructor of 490 assume that all the students have had Math 151? And of course, yes, because you have to have Math 151 to have the prerequisite 220. So this property is called the transitive property. Our next example is of a binary search tree. Now, think of each vertex as a data point, and you want to locate a particular data point in your data. So for example, suppose you want to locate the data point number 15. So you start at number 8, and you traverse the tree until you find number 15. But the way the data is structured, what you do at vertex 8 is you say, is 15 larger than 8? Or is 15 smaller than 8? Since 15 is larger than 8, you go to the right. That places you at 12. So you say, is 15 larger than 12 or smaller than 12? 15 is larger than 12, so you go to the right, and that places you at 14. 15 is larger than 14, so you go to the right, and you find 15. So the idea is, at each vertex, you either go to the right or to the left, and that's why it's called binary. You only have two choices. And in this case, you always go to the right if the number you seek is larger, and you go to the left if the number you seek is smaller. So if you think about the structure of the tree, compare that to a different kind of directed graph. Suppose that these 15 were just in a straight line, 1 to 2 to 3 to 4, say in increasing order. Then if you were looking for data point number 15, you would have to traverse the entire line. until you got to 15. But with the data being structured in this way, we only traversed 3 edges to get to 15. Let's take another example. Suppose instead of being numbered, suppose we're looking for a name, a particular person, say a customer, and all of the names are in alphabetical order. So to find that name, we're going to write a computer algorithm that first goes to the middle of the alphabet. Let's say we're looking for the letter P, because we're looking for Mr. Peterson. If where we land, we say is P to the right, or is P to the left of where we are. So if we landed at L, we would say P is to the right. So once again, from L to the end of the alphabet, we go to the middle. If we land on P, if P happens to be in the middle, then we're done with finding the first letter of Mr. Peterson. But if it's not P, then it's P to the right or it's P to the left, and so forth. So by structuring the data where you have 2 choices, to the right or to the left, then you cut down the number of times that you have to visit a given vertex or a set of vertices before you find what you're looking for. So a binary search tree is used a lot in designing efficient search algorithms in computer science. So a binary search tree is an example of a directed graph that's highly used in computer science. And unlike the other 2 examples, which can be thought of as a visualization tool, the binary search tree does not use visualization, but rather it is used to give structure to data and then make that data more accessible. Our next example is a Markov model. In a Markov model that, as illustrated here, the relationships, again, are not necessarily symmetric, and so we have an indicated direction of the relationship. And notice in this case, we also have loops. So we have directed, a bull market is related to itself, for example. So in this example, you could say we have a multi-digraph with loops. So we'll end this lecture with a silly example. In this case, the vertices are labeled dork, geek, nerd, and tech. And since there's a directed edge from nerd to geek, and also a directed edge from geek to nerd, the implication is if you are a nerd, you could be a geek, or if you're a geek, you could also be a nerd. But notice that if you're a nerd, you could be a tech. If you're a geek, you could be a tech. But there are no directed edges from tech back to nerd, geek, or dork. The implication being that if you're a tech, that does not imply you're a dork or a geek or a nerd. Seems to me this was probably a digraph created by a tech. What do you think? So in this lecture, we looked at some classical examples of digraphs. We saw an ecosystem and a prerequisite digraph, and we also talked about the binary search tree, which is a highly utilized digraph. We saw a picture of a Markov model, and we threw in a silly example too.